Hello. Right, so I would like to tell you about this recent result by Panteleev and Gleb Kalachev called Asymptotically Good Quantum LDPC Codes and Locally Testable Codes. So I'd like to in particular tell you what these terms mean. I should also mention that just the second half of this result, Asymptotically Good Locally Testable Codes, was recently called by Lance Fortnow the greatest complexity theory result of 2021. And this paper achieves it and also achieves at the same time asymptotically good quantum LDPC codes, which is also a tremendous breakthrough result. So perhaps this is doubly the greatest paper in complexity theory of 2021. Okay, so I originally gave this talk at Oberwolfach last month to some complexity theorists. And in fact, it was just after Rita Merritt gave her talk about the independent paper that also achieved asymptotically good locally testable codes. That was joint with Evra, Livna, Lubatsky, and Moses. And so I even tried to kind of make some of the slides and notation similar to her talk. So perhaps if you see that talk elsewhere, you can take a look at this one following it. Okay, so I won't try to actually prove anything in this paper, but I just hope to state the main definitions and state the construction that is achieved in this paper. Okay, so let's dive into it. So first of all, what is an LDPC code? Let me just tell you about classical error correcting codes, LDPC codes, low density parity check codes. An LDPC code on n bits is a kind of linear error correcting code over F2. We're only going to be talking about codes over bits here. And it's defined by a bunch of parity checks, which are depicted as these squares here. And each square is attached to, let's say, at most W or exactly W different bits. And W is to be thought of as an absolute constant. So this is the low and low density parity check codes. And these parity checks, check whether the XOR of the bits that they're adjacent to are equal to 0. Okay, so in order to be a code word, you have to pass all the parity checks. So for example, this green string 110011 is a code word because, for example, this parity check here is satisfied. It touches 1, 1, and 0. That adds up to 0 mod 2. Parity check, it touches this 1 and this 1. That adds up to 0 mod 2, etc. Okay, so the distance, the minimum distance in LDPC code is the least weight of a non-zero code word, which means a least weight of a non-zero labeling of the n bits that passes all the checks. And you would like this ideally to be a constant fraction of n. And the dimension of the code is the number of bits in the code minus the number of checks. So these will be linear codes, and therefore a good code should have a dimension which is also a linear fraction of n. So the so-called asymptotically good codes are codes that have a linear distance and a linear dimension as well. And they're LDPC codes if also these parity checks involve at most a constant number of bits per check. Okay, so that's the definition of an LDPC code, and we've long known that there exists an asymptotically good LDPC codes, and we can construct them efficiently. Now let me tell you what is the definition of a quantum LDPC code. Now I'll not really explain how it's code for qubits or anything, but I'll just explain it like it's two classical LDPC codes with a certain property. And I won't get into the details, but I mean, it's known that if you want a quantum LDPC code, it suffices to construct these two kinds of classical LDPC codes with a certain property. So a quantum LDPC code has some bits, again, these are actually the qubits. And then it has two sets of parity checks. These blue ones we'll call the Z checks, and the red ones are called the X checks. This refers to X and Z Pauli operators in quantum land, but we don't need to know what those are for this talk. And these should both be LDPC codes in the sense that both the blue checks and the red checks here should have constant degree. And in order for them to be a kosher LDPC quantum code, you can't just have any two classical codes. They have to satisfy some kind of orthogonality condition. And I'll mention what that orthogonality condition is on the next slide. But assuming they satisfy it, then you get a quantum LDPC code. And the dimension of the code is, as before, the number of bits minus the total number of checks. So minus the number of Z checks and also minus the number of X checks. Okay, so we again want this to be a linear fraction of n, the dimension. So what is this orthogonality property? The orthogonality property, one way to say it is the following. Your two LDPC codes should satisfy this. Take any blue check, such as, for example, this square, and imagine like sticking a 1 on it and propagating this 1 out to the neighbors of the blue check. So I've written a 1 at this neighbor and in this neighbor. And then further imagine propagating all the 1s written on your bits out to their neighboring red checks. So this 1 came down here, and this 1 came down here to this check, and also to this check. And the orthogonality condition requires that when you do this 2 levels of propagation, then at every red check, the sum of the bits that gets propagated to it, mod 2, should be 0. So we're happy here. This red check got 2 1s to it, so that adds up to 0 mod 2. But we're actually unhappy here because this red check got an odd number of 1s. So actually, these two blue and red codes here do not constitute a valid quantum LDPC code, although I drew them, because they fail this orthogonality condition. Okay, so that's the orthogonality condition. It's also equivalent if you did it the opposite way, like started from every red check, checked at its neighbor. If you propagate to its neighbors and you propagate to their blue neighbors, that everything adds up to 0 mod 2. This is equivalent, so you can check it either way. Okay, so if you're going to design a quantum LDPC code, like you need to design 2 LDPC codes, classical ones, with this kind of special property. So in particular, if you notice, one thing this means, if you have a quantum LDPC code, is that for every blue check, if you put a 1 on it and propagate that out to its neighbors, the result, when you put 0 elsewhere, is going to be a code word, a classical code word for the red LDPC code. This will happen for every blue check. But also, if it's an LDPC code, the blue one, then all of these code words that you get by just sort of propagating from a single blue check are of Hamming weight W, or at most W, which means that the red LDPC code at the bottom will have plenty of code words of extremely low Hamming weight. They'll have plenty of code words of Hamming weight at most W. You might think, oh, well, this is a big problem because we want our codes to have linear minimum distance or linear Hamming weight for non-zero code words. Well, the resolution of this is that the distance for a quantum LDPC code is also defined in a special way, which I need to tell you about now. So given these 2 orthogonal LDPC codes, the quantum distance is maybe not the first thing you would think it is. Rather, what you need to do is look at the least weight of a red code word, but don't go over all non-zero code words. Only go over the code words that are non-zero up to toggling blue checks. Now, when I refer to toggling a blue check, I refer to the process of like taking a blue square here and toggling mod 2, or like adding 1 mod 2 to all its neighbors. Okay, so in fact, I got this particular green code word here, 010010, by starting at all zeros and just toggling 1 single check. And the point is, for the purpose of computing distance, you do look at the minimum distance of a red code word, but you discount any code words that you can get by toggling blue checks. I mean, from 0. If like you can toggle a code word down to all zeros by toggling blue checks, then you don't have to count it for the purposes of distance. So you want to look at the minimum weight of any string that's a red code word that can't be toggled down to all zeros by toggling blue checks. So this should be large, and it's not symmetric, so you also need the vice versa condition. You also need that you're hoping that all blue code words that can't be toggled down to the all zero string by toggling red checks should also have linear Hamming weight. Okay, so that's the notion of quantum distance. Okay, so I defined quantum distance, and what is a quantum LDPC code, and what is quantum distance, and what is the dimension. And let me now show you an example. In fact, the most classic and famous and original example, the toric code due to Kalachev. And possibly, the first time quantum computers are built with some level of error correction, probably this toric code will be the one that's used. But we're going to envision designing much fancier codes. Okay, so in the toric code, there's a parameter, capital L, which in my picture is 4. And how do you get it? First, you draw like an L by L torus, well, sort of an L by L grid, but you should make this grid and identify the vertices on the right side with the vertices on the left side, so it wraps around horizontally, and also identify the vertices on the top side with the vertices on the bottom side, so it wraps around vertically. So even though it looks like it's 5 by 5 in this picture, it's actually 4 by 4 due to this vertex identification. And here's the situation. The bits are actually going to sit on the edges in this torus. And the red checks, or I think they're called X checks, will sit on the vertices. And the blue checks, which remember the Z checks, but never mind, the blue checks will sit on the faces. Okay, so, what is the incident structure? Well, the blue check checks all 4 incident edges, these are the bits, and also similarly the red checks, which are the vertices, check all 4 incident edges. So the W for this toric code, the low and low density parity check, is 4, because every face touches 4 edges and every vertex touches 4 edges. It's just like an unfortunate coincidence here that capital L is also 4 in my picture. That's just what I was able to draw. And generally, you should think of L as like much bigger than 4. It's like a growing parameter. But the W for this code will always be 4, which is great. I mean, that's very low density. So now we have to think about what is the distance and what is the dimension of this quantum LDPC code. Oh, actually, there's one more thing we need to check. First thing we need to check is that it's a legitimate quantum LDPC code in the sense that this orthogonality condition holds. So let's check that. So remember, how do we check the orthogonality condition? We take a blue check, which in this case is just a face or a square, and we imagine sort of writing a 1 on it, and then like toggling all its incident bits. So these are the incident 4 edges. And then we kind of propagate those ones on the edges to their incident vertices, which are the red checks. And you see, when we do this, propagation process, every vertex gets an even number of 1s. It adds up to 0 mod 2. So the vertices that are incident to the square that we toggled get 1 plus 1, which is 0. And all the other vertices get nothing propagated onto them, so they also have 0. And therefore, this is a legitimate quantum LDPC code. And in general, a lot of ways, a lot of quantum LDPC codes that have been constructed in the past have been constructed in this way out of like chain complexes or other topological constructions that kind of make this orthogonality condition hold sort of automatically. Just for future reference, let me add one other thing, just because it'll come up. Notice that there's sort of 2 different kinds of bits in this construction, the horizontal edges and the vertical edges. And this is a feature that kind of also sometimes recurs in constructions of quantum LDPC codes. Okay, so the easier thing to check for this code, dimension and distance, is the dimension, because you just have to count things. So the dimension turns out to be 2 for every value of L, which is extremely bad, by the way. I mean, it kind of means that you can only encode like a constant number of message bits or logical qubits. The way to check that it's 2 is the total number of bits is like 2L squared, because there's basically L squared horizontal edges and L squared vertical edges. So that's the 2L squared. And then you're supposed to subtract the number of red checks and also subtract the number of blue checks. So it would seem that there's L squared red checks and L squared blue checks, but actually, you can kind of check that if you add up all, let's say, the red checks, like mod 2, they cancel out to 0. So actually, one of them is redundant. It's linearly dependent. So there's really only L squared minus 1 linearly independent red checks. And similarly for the faces checks, so the final dimension is 2L squared minus L squared minus 1 minus L squared minus 1, which is constant 2, which is, hey, at least it's not 0. It's strictly positive for all L. So that's not great, but it's non-trivial. And now what about the distance? So remember, you need to have both the red distance be large and the blue distance be large in order to have good quantum distance. Everything is kind of dual to each other here. This is another feature, by the way, of quantum LDPC codes, and most especially this PK construction. Like everything has like a twin. Everything has got like a dual thing going on with it. So right, so it's going to be sufficient to try to figure out what is the red distance in this toric code. Now, at first you might think, oh, there's these very low weight code words. There's like red code words of weight 1, which is true. Because, for example, if you just take all 4 edges in a square and label them by 1, then this is a red code word because it passes all the red checks. In other words, for every red vertex in this picture, it will be incident on an even number of 1s. So some red vertices are far from your chosen from this chosen square, and therefore they're incident on 0 1s. But for this particular chosen square, its corners are incident on an even number of 1s. Which looks bad, but remember this doesn't count because you can achieve this code word of 4 1s by toggling a blue face. Or, similarly, if you toggled, like, let's say 3 blue faces like this, you would get this code word that kind of looks like a loop. I mean, it's the code word that has 1s on these 1, 2, 3, 4, 5, 6, 7, 8 edges, which maybe seems bad if L is large, you have a code word of size 8. And you can see here that every red vertex is incident to an even number of 1s. But again, this one doesn't count because it's achieved by toggling blue, the incident bits or edges of some blue faces. Okay, so these kinds of code words, red code words, which look like loops topologically, don't count for figuring out the distance. So what is the red distance? Well, there are some loops. There are some red code words which cannot be achieved by toggling the edges incident to blue squares. So, a typical one, in fact, the lowest Hamming weight one, is, let's say, a code word that has 1s on all the horizontal edges that form like a loop. And remember, this wraps around. Imagine if you label all these black horizontal edges on, let's say, this middle row with 1s, and every other edge is labeled by a 0, then this is like a red code word in the sense that every red vertex will be incident to an even number of 1s. And therefore, it's a red code word of Hamming weight L. And it's not hard to check that you cannot achieve this code word, this 1s labeling a horizontal loop like this, just by toggling the boundaries of some blue faces. For example, if you, toggle a horizontal sequence of blue faces, you'll get 1s labeling 2 parallel horizontal edges. Okay, so there's no way to get this one. So this is like a red code word that you have to count against yourself for the purposes of distance, and its Hamming weight is capital L. And this turns out to be minimal. So the blue distance is also L. So for example, again, if you choose these if you choose these 4 black edges, put 1s on them and 0s elsewhere, then it looks like a blue code word of Hamming weight 4, as every blue face would be incident to an even number of chosen black edges. But it doesn't count because you get this one by toggling this red vertex. But there are some blue code words of Hamming weight L, which can't be achieved by toggling red vertices. So for example, if you choose a bunch of horizontal edges like this that go down a column, this is Hamming weight L, and it's a blue code word that you can't get by toggling red vertices. Okay, so long story short, the minimum distance in this toric code is L, and the number of bits is 2L squared. Okay, so basically the minimum distance in this toric code is the square root of the number of bits, up to a constant factor. As we saw, the dimension was 2. So this is my giant slide, very partial history of results on quantum LDPC codes. I've got a column here for a distance and a column for a dimension. There's no animations here, everything's spoiled, so you can just pause this frame and read everything, but I'll go through it. And on the left, we have some of the previous constructions. And in these 2 columns, distance and dimension, I omitted the constant factors, big O, almost everywhere. Okay, so the toric code, as we saw, has distance proportional to root n, and dimension 2. So it's got okay distance and terrible dimension. Okay? Just a reminder, an asymptotically good code will have distance and dimension both proportional to n. Okay, so for a long time, actually, after 97, for 5 years, there's some thought that perhaps, in these quantum LDPC codes where everything needs to have a twin and this orthogonality property, there's some reason to imagine that you couldn't possibly have any distance bigger than square root n. But this was shown to be breakable, the square root n barrier, by Friedman, Meyer, and Lowe in 2002. Used a construction based on hyperbolic geometry. They got distance that was bigger than square root n by a polylog factor, and it also had dimension 2, I think. I hope I got all these details on this history slide correct, by the way. But I don't 100% guarantee it. Okay, so much later, maybe 12 years after the Toric code, Tillich and Seymour made the first code. It's kind of based, well, it kind of generalized the Toric code, which is sort of like, in some ways, like a product of two cycles. Tillich and Seymour showed that if you took some kind of tensor product of two asymptotically good LDPC codes, which we've long known to exist, you could get quantum LDPC codes with dimension proportional to n, so that's excellent, and distance proportional to root n, which was more or less the best known at the time. Okay, flash forward like another 11 years, and there's this very, very beautiful paper by Everett Kaufman and Seymour, which showed how if you took a tensor product of like a good locally decodable, sorry, not locally decodable, LDPC classical code and a high dimensional expander, you could break the root n distance barrier again by a log factor and get like a large dimension, pretty large dimension, square root n. And this paper had many other like beautiful properties, including like an efficient quantum decoding algorithm. Great. Later, Kaufman and Tesler that year showed that by doing some iterated tensor product of high dimensional expanders, you could get similar results, but boosting the distance of the quantum LDPC code up to root n times any polylog. Then I also had some work in the same year, joint with Matt Hastings and Jungwon Ha, where we showed some kind of like different, like twisted product or fiber bundle code that you could get out of one classical LDPC code and one cycle code, could achieve distance that sort of substantially broke the root n barrier. It got distance n to the 0.6 divided by some polylog factor, and dimension n to the 0.6 divided by some polylog factor. But just a few months after that, the heroes of our story, oh, I see there's a little spelling mistake. Sorry, Pavel, should be an extra E. Oh, in this citation. Oh, and these are my old slides because I see there's another a typo here. This should read n to the 1 minus epsilon over 2. Okay, so maybe it doesn't seem like a big deal, but the trade-off that's here. So Panteleev and Kalachev in 2020 took some kind of lifted product of two, well, rather a Sipser-Seelman base code and a cycle graph. And they achieved distance n to the 1 minus epsilon over 2 over log n, and dimension n to the epsilon times log n for any epsilon between 0 and 1, including epsilon equals 0, which in particular meant distance n over log n and dimension log n. So that was pretty awesome because like it got almost linear distance, n over log n, and even with growing dimension, like log n. Or if you take epsilon to be real close to 0, like, I don't know, 0.1, then you would get distance n to the 0.95 over log n, pretty close to linear, and dimension n to the 0.05, or whatever I said, n to the 0.1 times log n dimension, which is a polynomial dimension. So that was an awesome result, but had more in store for us. After that, I'd like to mention that Breichmann and Eberhardt kind of generalized the notion of products in this Panteleev and Kalachev paper, and they achieved a code with distance n to the 3.5, or sorry, n to the 3/5 and dimension n to the 4/5, which actually matches this trade-off for a specific value of epsilon. Right, yeah, because if you take epsilon to be 4/5, you get n to the 4/5 here, and with epsilon being 4/5 and the corrected value of epsilon over 2 here, you get n to the 1 minus 2/5, which is n to the 3/5. Okay, so it wasn't actually better than this in some sense, but it was explicit. This one was a randomized construction, and they had new ideas for how to make products of smaller codes. And indeed, they kind of conjectured that you could potentially get asymptotically good quantum LDPC codes by taking like some kind of product of some kind of expander codes. And indeed, this was proven in the paper that I'm telling you about, Panteleev and Kalachev from just a couple months ago. Now, it's not like they, Brickman and Eberhard, by the way, like conjectured like literally the exact construction in this PK paper. Maybe they kind of conjectured the framework, and it was up to P and K, Panteleev and Kalachev, to pull it off. And as I'll now try to explain to you, their construction was some kind of lifted product of two Cayley-graph expanders together with some random base codes, some Sipser-Spielman type codes, where the base codes have some special property. And not only do they get linear distance and linear dimension, but they can even make the dimension arbitrarily close to n, which is even awesomer. Okay, so this red result is what I want to basically state for you in the rest of this presentation. At the same time, also in this paper, they basically showed that if you took their construction of these quantum LDPC codes that are asymptotically good, and you just threw away half of them and retained only like the blue checks, you would get the so-called locally testable LDPC codes, which are also asymptotically good. Actually, you have to adjust the parameters a little bit. So they have one parameter setting for their quantum LDPC codes and like a slightly different parameter setting for their locally testable LDPC codes, classical LDPC codes. But basically, the same construction and practically the same analysis gives you these asymptotically good LTCs with constant relative distance and constant dimension and even dimension almost as large as a half times n. And achieving asymptotically good classical locally testable codes is like a very, very long-standing open problem in complexity theory and coding theory. A lot of people thought it was not even possible. Maybe it opens the doors to PCPs of linear rate. And this LTC result was, as I mentioned, achieved independently by Dinur, Evra, Livnet, Lubotsky, and Moses with a similar construction. And actually theirs has even, in some sense, slightly better parameters because they can get their dimension almost 1. Almost 1 times n. But even getting dimension 0.00001 times n would be like an extraordinary achievement. So it's pretty impressive that both of these people got like actual explicit constants. Great. So I'm actually not going to talk about the locally testable LDPC codes at all, because I just want to focus on the quantum codes. But you can see talks elsewhere about these LTCs. And in some sense, the quantum LDPC construction is kind of like the Dinur LTC construction, except that like everything has to be more symmetric. So I mean, they just need to construct the LTCs in the classical case. So they have kind of like the blue checks, and like the red checks are not really a necessary component of the code. It just sort of helps them organize the red checks to ensure that we have like a locally testable code. But for the quantum LDPC codes, like everything needs to be perfectly symmetrical, and this is why the construction is like a little bit more involved, and perhaps also why they only get dimension close to a half. Okay, so my goal is to just state the construction, which is not, if I may say so, completely easy to read out of the paper. And there's also a chance I will not state it exactly correctly. I think it'll be like 95% correct in spirit, maybe even like 95% correct in details, but there's a couple of parts I'm a little flaky on, but you'll mostly get the gist of it, and hopefully this explanation will be mostly correct. Okay, so these quantum LDPC codes of Panteleev and Kalachev are some kind of product of Tanner codes. So first I have to explain to you what is a Tanner code. They're going to be expanding Tanner codes, in fact. Okay, so what is a Tanner code? It's a completely classical LDPC code that's like defined in a way that's a little bit more involved than the previous definition we saw. Okay, so in a Tanner code, you again draw a bipartite picture like this, where you have these like bits here, which will be the code word bits, and you'll have these checks, which will again depict as like blue squares. And let's now and for the future assume that like it's regular, so every blue check is incident on exactly W bits, where W should be a constant. And in the previous picture of LDPC codes, we just said that like, you're a code word, a green labeling down here of zeros and ones is a code word. If when you take these green bits and like propagate them or push them along the edges to the incident checks, each check gets bits that add up to 0 mod 2. So each check is like checking just the sum mod 2 of its neighbors is 0. But in Tanner codes, you do something more sophisticated. So in Tanner codes, you have like a so-called small code or like a little code, script C, another code on W bits. Okay, remember W is like a constant. So you have this teeny tiny other code on W bits. And we'll say that C is defined by its parity check matrix, which I'll call little h. And this parity check matrix will have like epsilon times W rows, or like epsilon times W parity checks. And now in the picture, you're going to be a code word. This green labeling down here is going to be a code word in this Tanner code. If for every blue square, if you look at the W bits on which it's incident, so in this case W is 4, so if you look at the like 4 bits on which it's incident, in this case 1, 1, 0, 1, it's not that they should add up to 0 mod 2, it's that they should be a code word in this little code C. And what does it mean to be a code word in this little code C? It means you should satisfy all the parity checks in H. So this 4 bits inner product with each row of H should be 0. Okay. Now this is actually, even though this Tanner code looks like a different construction because you're checking that the bits here now fall into a certain code rather than just that they add up to 0, this is actually still a standard LDPC code, as I will now describe for you. So why is that the case? Well, you can turn it into the actual LDPC code of the type I described before by sort of blowing up each big blue check here into epsilon W, or however many rows little h has, in this picture 3, little checks. So you see, just for each parity check in H, let's say this last one, which is 0, 0, 1, 1, this row will correspond to this new little check. And basically, all these checks were formerly incident to these 4 rows, and instead you just make this little blue check incident to those neighbors where there's a 1 here. So this row is 0, 0, 1, 1. It's supposed to say that the parity of the last 2 bits is 0. So that just means that you connect up this little light blue check just to the last 2 of the 4 bits. Okay, and so similarly for each row of H, you make a little check here that's just like an XOR check, where you connect it to all the neighbors where there's a 1 in the corresponding spot in the associated row of H. Okay, and then when you do that for every one of these big blue checks, replace it by epsilon W checks, or however many rows there are checks here, you get the old kind of classical LDPC code. Okay, so it's just a specially constructed LDPC code that we're going to draw in a certain way. Actually, there's yet another way to look at these Tanner codes, and let me try to describe it like this. We're going to now depict a Tanner code like before, with these big blue squares representing the checks. But what we're going to do is we're going to, instead of just having this code C in the back of our mind, we're going to decorate each of the 4, or in general W, edges incident to a check by the W columns of H. Okay? And then the way to think about this check now is that you kind of, again, to decide if a green labeling of 1s and 0s down at the bits is a code word, you kind of propagate up the 1s, and then you multiply them against these columns that are written here, and add up the columns, and you check that the result is 0 in the sense of being the 0 column vector. Okay, if you think about it, that's the same thing. So to say that 1 times H1 plus 1 times H2 plus 0 times H3 plus 1 times the last one, H4 or HW, is the all zeros vector, is really to say that 1, 1, 0, 1, when multiplied against this matrix gives you all 0. So it's really the same thing as saying that this 1, 1, 0, 1 satisfies all the parity checks that are these rows. Okay, so you can pause here if you like to just understand that this is yet a third way to describe the Tanner codes. Sort of, you label the incident edges by the columns of this matrix H, and then the check is this propagation thing but now you're like adding up vectors to see if there's 0 mod 2. Okay, so that's a Tanner code. Now get ready. We're going to talk about quantum Tanner codes. Okay, so what will be quantum Tanner code? And this looks real complicated, but this is what we're going to get into. Okay, so in a quantum Tanner code, we still have all these bits before. And since it's supposed to be a quantum LDPC code, we're going to have these like big blue checks on top like before. We're going to have these big red checks on bottom like before. And this is really going to be like a quantum LDPC code like as before if you like blow up all the big blue checks into like little checks like we did for Tanner codes. But just take my word for it that that works, and I'll just directly describe it to you with the vectors. So like with Tanner codes, we need to have like these little constant size codes, and just because everything needs to have like a twin in this construction, we're actually going to take two potentially different little codes, which I called like blue H and red H. And just in case, I don't know, you can't tell the difference between red and blue, like I'm always putting like underline as well for the red side. So we have like H and H underline. And for the quantum LDPC codes, it's actually, I think, ultimately okay for H and H underline to be the same. I think for the LTC construction, you don't want them to be the same. But either way, it's definitely conceptually better to allow the possibility that they might be different. So I really want to imagine that like H and H underline are two different, little constant size codes, even with like differing numbers of parity checks, epsilon W and epsilon underline W. Okay, so we have H's columns, H1 through HW, H underlines columns, H1 underline through H1 underline W. Okay. And things are still not simple in the PK setup because there are going to be two different kinds of bits. And actually, this may be familiar to you from the toric code. Remember the toric code? There are also two fundamentally different kinds of bits or qubits because there's like the horizontal edges and the vertical edges. Although it was symmetric there, there still had two different flavors. In the PK construction, there's also going to be two different kinds of bits. And I am temporarily going to call them the rare bits and the common bits, but I'm going to change those names later. And I also am not yet telling you at all like how we're going to come up with the incident structure, which blue squares and which red squares are incident to which rare bits and which common bits. That's all going to come later, but I just still want to tell you like what is going to be this quantum Tanner code picture. Okay, so the setup is going to be that for every blue square, it'll have exactly two neighboring rare bits, and these will be labeled by the same red column, like H underline J and H underline J. Okay, and they'll actually be like W different kinds of blue checks, and so like this will be like a J kind of blue check, and that's why these are both labeled with J. And a blue check will also have exactly W sort of checks into the common bits. And its W checks into the common bits will always be labeled with just like blue H1, blue H2, up through blue HW. These blue squares will always have like W plus 2 checks, these W1s into the common bits, which are labeled H1 through HW, and the 2 checks into the rare bits, which are labeled by H underline J for some particular J associated with this blue check. Okay. And it's sort of all just the reverse for the red checks, you can see here. Okay. Not only that, I'm sorry to say, it's even more complicated because these common vertices here, these so-called common vertices, will be labeled by bits, but these so-called rare vertices will actually be labeled by constant size matrices of bits. Okay, so these rare sites will be labeled by matrices of rectangular matrices that are like epsilon W high and red, underline epsilon W wide. Okay, so each site here will actually carry like, epsilon squared W squared bits of the code, and each site here will carry just one bit of the code. And altogether, these will form the bits of the code. And you still have to take my word for it that if you like really think about it for long enough, like this still corresponds to the original definition of a quantum LDPC code, where you just have sort of the regular checks and the regular bits, but like this is the sort of tannerized version of it. And I haven't even told you like what the checks are, but basically they're the only logical thing that you can imagine. So how do you decide if a labeling for these green sites or vertices is a code word? Like, is it a blue code word and is it a red code word? Well, like, what does it mean for a labeling here to pass the blue checks? Remember, labeling here is like one of these matrices of bits for each of the rare sites and like just a single bit for each of the common sites. And basically, as I said, the checks are like the only things you could imagine. So for the blue checks, you're going to be checking that a bunch, for this particular blue check, you're going to be checking that a bunch of vectors of height epsilon w add up to 0. And which vectors do you add up? Well, you look through all the bits here in the common sites, and whenever you have a 1, you like add up the associated vector on the edge, just like before. Okay, so that gives you some of these height epsilon w vectors to add up. And you also need to add up some more epsilon w height vectors from these two edges. And how's that going to happen? Well, there's only one thing that you could imagine, right? So these guys here are labeled by matrices of bits that are epsilon w high and like red epsilon w wide. And you have like a red epsilon w high vector here and here. You just like multiply this matrix by this vector, and it'll give you a vector of height epsilon w. Okay, so like in the natural way, like the combination of like the matrix labelings here and these two red height vertices gives you two blue height vectors. I said vectors when I meant to say vertices when I meant to say vectors. And you also like add up some more blue height vectors by multiplying these ones against the zeros and ones that are here. And it's all analogous on the red side. So in this way, you can figure out like when some labeling to the green sort of vertices here constitute like a blue code word, and also when it constitutes a red code word. And you'll just have to check for yourself that like the quantum LDPC code that we construct in this way really does satisfy this orthogonality condition that you need to be a legitimate quantum LDPC code. I really just want to sort of state the construction here. I still have not told you, by the way, how the incidences work, and this is also very important. Like, how do you choose, like what, sites down here, or vertices down here, each check is connected to. But once I tell you that, then the code is defined because, and once the little blue code and the little red code defined by H and H underlined are also specified. Once that's all specified, that specifies the quantum LDPC code. Okay, so now I have to tell you the incidence structure, like which checks, which blue checks are connected to which rare sites and which common sites, et cetera, et cetera. Okay, so this incidence structure arises from expander graphs, much like in Sipser-Spielmann codes. And you need actually expander Cayley graphs in order for this to work. You need regular constant degree expanding Cayley graphs. Just your favorite expanding Cayley graphs are fine. So for example, like the Margulis / Lubatsky-Phillips-Sarnak Ramanujan graphs are okay. So those are explicit ones that you can use. And so for the scalar graph, you'll have some vertex set G, that's a group, and you'll have some set of generators A of size, constant size of size W. And your generating set should be closed under inverses, so that's fine. So as I said, Margulis, LPS, Ramanujan graphs are okay. This picture is a little bit bogus because I guess W should be even if like these generators A are to come in pairs like A and A inverse, but anyway, I just wanted to draw a 3 regular graph. Okay, so you have a W, you start with a W regular expanding Cayley graph. And you take the double cover. As I said before, everything has a twin, a dual object, a doubling in this construction. You need to then take the double cover of this expanding Cayley graph. What does that mean? So it's a bipartite graph where you have like 2 copies of G. You have 2 copies of the old vertex set, which I'll maybe call G0 and G1. And whenever you had an edge between like 2 vertices on the old graph, now you have an if it was between U and V in the old graph, then it's between like the left side copy of U and the right side copy of V now. So in particular, we can say this a little bit more explicitly. How do we name the vertices in this double cover? Well, we name them by a pair of objects. One, a little g from the group. That corresponds to like a vertex in the non-double cover, the original graph, together with like a bit, which I'll call sigma, which is either 0 or 1, that specifies whether you're like on the left side or the right side. How do you name an edge in this double cover graph? Well, like an edge, we'll name it by like a group element G, which we'll think arbitrarily as being on the left side, so like on G0, together with a generator name, little a sub j from the set A. And that connects you from like little g on the right-hand side to, oh boy, either aj times g or maybe g times aj. I think that's another tricky thing in this paper. You have to get like all at least correct whether you're multiplying on the right or multiplying on the left. There's like a 40% chance I'll get it wrong every time I need to get it one way or the other. Okay, so that's the definition of, okay, this is our double cover of our W regular expanding Cayley graph, and we will need this in order to describe the incidence structure of this like Tanner quantum LDPC code. And now the construction is, here we go, it's some kind of product of the double cover with itself. So again, doubling, duality, the twins. So some kind of like G lifted product or G twisted product, if you will, of the double cover with itself. Okay, so let me explain what this is. Again, this is defining the incidence structure. So what are the like the objects in this G lifted product of the double cover with itself? Well, you kind of have like one, 2 copies, like one vertex, or okay, you kind of have like 2 objects from the original object. So you have either 2 things, each of which is either a vertex or an edge. They're kind of glued together with an element of G. So okay, let me just say it. The kinds of objects in this double cover product with itself are triples. Here's my parentheses. The first element of the triple is either a bit, sigma, or it's the name of a generator, a sub j. It'll be blue on the left. In the middle, you have a group element, G. And on the right, you again have either a bit or a generator, which I've written in red, like a sub k. And therefore, actually, there's sort of 4 kinds of objects. There's like the kind where you have like bit, bit on the left, generator on the right, generator on the left, bit on the right, or 2 generators. 4 kinds of objects in this instruction. So let's give names to them. So the kind where you have like a bit on both sides that look like sigma G and sigma underline. These are going to be our rare sites, but we're going to rename these rare sites for reasons you'll see soon to vertices. And on the other hand, let me skip to the bottom. When you have a generator on both sides, the objects that look like blue generator, G, red generator, these will be what we used to call common sites, but we're now going to call them squares. Okay, so actually, ultimately, the sites for our qubits will be these vertices and these squares. So it's a bit different from the toric code. Or the toric code, you're thinking of the bits happening on like the horizontal edges and the vertical edges. No, the way they're doing it here is the bits sit on like vertices and squares. So it used to be rare sites and common sites. And the other objects will be associated to, or they'll be our checks. So when you have a generator on the left, which I've depicted in blue, a generator on the left and a bit on the right, this will be called a blue check or also a blue edge. And when you have a red generator on the right and a bit on the left, this will be called a red check or a red edge. So we call them like vertices, edges, and squares when they're thinking about the incident structure of how the checks are connected to the bits or the sites. And well, we call them checks when they're thinking about them as kinds of generalized parity checks. Okay. So here I've just actually so far just named the objects for vertices, edges, like blue edges, red edges, and squares. I still haven't actually yet said how these things are incident to one another. But again, it's kind of like the thing that you would imagine if you had to guess. So let me try to explain this. Um, so now we're going to be talking about, our quantum LDPC code has some blue checks, some red checks, some vertices. These were the rare sites before, and therefore the vertices are now going to be labeled by matrices of bits. And the squares are like the common sites. These are going to be labeled by bits. So now it's a new thing. Squares get labeled by bits. Vertices get labeled by matrices. Okay, so what are the incidences? So let's start with a square in our new incidence structure. So a square, remember, is like a triple that looks like generator, G, generator. And it's going to be called a square because it's going to be incident to 4 edges. That's why it's called a square. And it's going to be incident to 2 blue edges and 2 red edges. Oop, there is a edit in the video here because I couldn't understand my own slides. And I think I've even changed the slides that are in front of you because I made these a while ago and I kind of forget them. And actually, it's very technical. I'm going to increase the probability that I have a detail wrong up to 100% here. But what I'm about to tell you is definitely almost correct. And maybe this will even increase my YouTube engagement. Like, write in the comments the correct version of what I'm about to tell to you. So we have a square like this, and it's going to be incident to some blue edges or blue checks. And these incidents will be all like common incidences, because remember the squares are like the common sites now. And for example, like a square like AJGAK, let's even look down here. It's going to be incident to some red edges that look like this. Remember, you think of this like pair AJ and G as an edge in this double cover graph that goes from like G on the left to AJ times G on the right. And so therefore we see down here these two vertices in the base graph are like 0 and G, that's the left endpoint of this edge, and 1 AJG, that's like the right endpoint of this edge. Okay, and on the other side, the incidences go the other way. So like, since it's GAK over here, on the right it goes to G0 and G times AK, or maybe AK inverse. I think AK inverse, but again, just to say if I got this exactly right, comma 1 here. Okay, and these are blue edges, and these are red edges, and these are the common ones, again, because the squares are the common sites. And let's say, for example, here we also have to write the vectors that we're decorating our edges incidences with. And since here we're kind of shifting around AK, we decorate these edges with HK. When we go from this square to these edges at the bottom, since we're changing around AJ, we decorate those edges with H underline J. Similarly, if you have like a blue check edge that looks like this, like AJ, comma G, comma sigma underline, it's going to be incident to exactly 2 vertices. And these are our rare sites, the vertices, which is why like each blue check edge is going to be incident to exactly 2 rare vertices, if you will. And again, since we're kind of going down from like AJ, comma G, comma sigma underline, both of these checks are going to be decorated with like red H sub J, the same J's here. So remember before, like, in these rare incidences, the vector decorating the edge is going to be the same one, the same column, like HJ. That's because like each check has its own like type. Blue check is like a J type blue check. That's why its 2 incident rare checks are HJs. And again, when we go down to like the sort of vertex incident on this edge, there's 2 of them. We can either put 0 or 1 in the first slot, and accordingly we put either G or AJ times G in the middle slot. Okay, so again, I think I kind of more or less got that right. It's very similar to this, but perhaps the detail is a bit wrong. Right, so in fact, modulo these technicalities, I've actually sort of now defined the whole code for you, except for specifying what these little codes are. But we've seen the whole incidence structure. Incidence structure is defined by this like product of two double covers of the expanding graph where like every check or edge is incident on two vertices and like a bunch of squares. And just a reminder, the squares, the common things are labeled by bits. The rare sites, the vertices, are labeled by matrices of bits. And all the edges are decorated by these vectors. Okay, so in principle, I have told you the construction modulo the choice of these two little codes. I just want to put up these pictures from the Panteleev Kalachev paper. This one is trying to like illustrate the incident structure. You see it's got like a vertex here and a bunch of squares attached to it and some red and blue edges, which they call like vertical edges and horizontal edges. And this quite very much resembles the pictures that you see in the paper by Nonesuch et al. And their construction of classical LTCs that are asymptotically good. There's another picture from the PK paper that's like illustrating the local improvement algorithm that they use to prove the distance of their code. So just to zoom in on this like one more time to look at the local checks, like here is maybe like one blue edge or one blue check in their construction, which is an object that's labeled by like a blue generator and then a group element G and then a bit sigma underline. And it's incident to a bunch of squares, again, like the pages in the book in Nonesuch et al.'s language. These squares are labeled or indexed by, again, the generators that you would plug into the right-hand side to get the different square names down here. And the kth one is checked by the kth blue vector, h sub k. That's how this blue edge checks all of these squares. And remember, these squares are labeled by bits, so I've shown this like front-facing square is labeled by a 1. That means when you're doing this check here, you'll add up, because this is labeled by 1, you will add up h1 into your overall sum. The check is trying to check that this blue height vector adds up to 0. And for whatever page or square back here gets labeled by 1, you add up the associated blue h vector. And you also add in two more blue height vectors, epsilon w height vectors, that you get from this blue edge being incident to these two vertices. And these vertices, remember, are labeled by matrices of bits. Okay, so these are like, and the decoration for this blue edge check, which has an AJ here, is like the red HJ. And in the check, you multiply this red HJ vector against this matrix in the appropriate way. You'll get out like a blue height vector, an epsilon W height vector. Finally, you add those two blue height vectors you get from the two vertices together with all the blue height vectors you get out of the incident squares. And the check is that that adds up to the 0 vector of height epsilon W. So that's sort of the construction. Okay, so I'm not going to get into any proofs, but I'll just say some words about the proofs. The essential thing you have to prove is to analyze the distance, the quantum distance of this construction. Okay, let me just say that it is elementary. There's no craziness used in the proof. It's, combinatorics and stuff. Like a half a dozen pages. If you want to read the paper yourself, the key lemma is lemma 15. This is like the most main lemma in the whole paper. It's about 3 pages long that analyzes the quantum distance. And it is like very much like a Sipser-Spielman style like iterative local improvement argument that proves that like the distance is proportional to n. So how does it kind of go? You say, okay, suppose for contradiction, or suppose that you have a red code word that's of weight little of n. And what we want to show actually is that by toggling blue checks, you can turn this red code word into the all zeros code word. And once you do that, then you say, oh, this is one of the ones we don't have to worry about. So if you can prove that about all red code words of Hamming weight little of n, then you show that the only red code words that you have to worry about that don't toggle down to 0 have weight proportional to n, which is what you want to do in order to show that the red distance is linear. And then you have to say like, oh, everything is symmetrical, and so therefore we could make the same argument about the blue distance being big omega of n. Okay, and it's, it's like a Sipser-Spielman flavor analysis. So if you have like this red code word of weight little of n, Means, like you have a small enough collection of sites, like the vertices and squares, that the expansion properties that they apply, the expander graph has the property that you can only say that, sets are expanding if they're, sufficiently small compared to n, but we're assuming they're little of n weight. And then you have to look at uh, not just like sort of distance one neighbors of the vertices in the squares, but also like distance two neighbors. So it's a bit subtle, and you argue that these cannot be the ones that you get at distance one or at distance two cannot be like two clumped together by expansion. They have to sort of spread out. This is very vague, of course, but you can look at lemma 15 if you like. And finally, you use a special property of the base codes, H and H underline, to argue that by virtue of this like non-clumpiness, there has to be some blue check that you can toggle that will lower the weight of your code word. And then you can repeat this argument more and more and more. You have like an even lower Hamming weight red code word. By the expansion and the special property of the base codes, you argue that there is some blue check that you can toggle to lower the weight. And eventually you get all the way down to 0, and therefore realize that this is a red code word that you don't have to worry about. And the only ones contributing to the distance have Hamming weight big omega of n. Okay, so finally, I will just say, once again, I'll just state what is the special property that you need out of these two little codes. And it's sort of like a bespoke property that they just like look into their analysis of their iterative decoding algorithm, figure out exactly what combinatorial property of the H and H underline that they need, and then they just hope to have this property. And it's some kind of robustness property of like some kind of tensor-like code of H and H underline. I'll just tell it to you or read it to you. So let's let C be the code whose parity checks are H. And let C underlined be the code whose generator matrix is H underline transpose. Which maybe is not what you expected, I would say, but again, all this like duality and twinning and whatnot. And now we're going to make a new code with W squared bits that are going to be written as W by W matrices. I'll call this code just CC underline. The code of all matrices X that are W by W, such that following properties: if you left multiply X by a row of H, then the resulting row is a word in C underline. Okay, so this is some kind of something similar to a product code or a tensor product code, but like there's an asymmetry between like C on the left and C underline on the right. One you have the parity check on the left and the generator matrix, or the dual code on the right. And finally, when you're going through lemma 15 and you're in the final guts of proving the iterative decoder, you need the following special property of all the non-zero code words X in this code CC underline. Remember this, these code words look like W by W matrices. You need this property that if you have a non-zero code word and it's possible to delete at most W to the 2/3 rows and columns from it and make its Hamming weight really quite small, smaller than W to the 7/6, which really is small because remember the number of bits in X is W squared, so W to the 7/6 is like a smaller power. Then it must be possible to add a code word from C to a row, or a code word from C underline to a column, in order to decrease the Hamming weight of X by some linear proportion of W, 0.001 W. Okay, so this is like the exact property you need out of the these two codes, H and H underline. And then you just prove that a random pair of codes has this property. And in fact, you actually need that when you choose H and H bar at random. C and C bar underline have the property, and also if you switch them, C underline and C have this property. And it's a standard kind of random construction argument. And since these are constant size codes, it's explicit. I mean, once you argue that they exist, then you can just have them because they're constant size objects. Okie dokie. So I will now wrap up because I've in principle told you all the ingredients in the construction. Let me just make a final few comments. First of all, as I said, I've only described for you the quantum LDPC codes that Panteleev and Kalachev construct, but you can also get asymptotically good, locally testable classical LTPC codes out of this. As I mentioned before, in order to do this, you actually have to change the construction a little bit. So instead of taking like H and H underline to both have like some small epsilon times W many rows, you need to make one of them have like 1 minus epsilon times W rows, and the other one have epsilon W times rows. And then once you do this, half of the overall quantum LDPC code is your asymptotically good LTC of dimension close to a half. And the argument for this, above and beyond what you need for the quantum analysis, is just like 2 paragraphs. And to be completely honest, I don't exactly know why they merely get rate a half or close to a half rather than rate near 1, like in the Dinur, Evra, Livna, Lubatsky, Moses paper. I think it might be because of the use of double cover, but I'm not sure. So that's one little thing that could be improved upon. Another thing that you could try to improve upon is you might want to get asymptotically good quantum locally testable codes. So there's also a notion of locally testable quantum LDPC codes. And Panteleev and Kalachev actually don't get this. In order to get this, you basically need to make your asymptotically good quantum LDPC code where each of the 2 halves are classical LTCs. And as mentioned, like in the PK construction, only one of the 2 halves is a classical LTC. So they currently don't know how to get asymptotically good quantum LTCs. And they also don't currently know an efficient decoding algorithm for their quantum code, although it seems plausible that you could get one, but this is still open. And that's it. That's my final comment. So I hope it was somewhat understandable, and hopefully we can look forward to efficient decodability and asymptotically good quantum LTCs, and maybe even linear rate PCPs in the near future.
I got some time to explain the true brain of a rhyme writer. Some take the stance of a gunfighter. Others inject intellect or self-respect, or simply kicking words for a tight paycheck. What they neglect is creative aspects and control. The sounds and words originate.